are discussing today one of the important most chapters of electromagnetism, that is electromagnetics. The very first part we are taking up, that is electromagnetism. That in other words, magnetic effects of electric currents. About this particular chapter, before taking up some of the applications, let me remind you few aspects. One is, every year few questions are given from this particular chapter at JEE level. So every one of you should be perfect and thorough with this topic, by all means one. And coming to the second aspect of it, what are the outlines of this chapter you have worked out? Initially, you might have taken up the direction of magnetic field produced due to the passage of electric current through a coil or through a straight conductor, whatever is the case. For that, right hand thumb rule or Maxwell's corkscrew rule you might have adopted. And till the end of this particular chapter, every one of you should be perfect with this right hand rule, right hand thumb rule in particular. That is the one which used to decide the direction of magnetic field, the direction of current, and so many other things are going to be rather taken up by looking to this right hand thumb rule. So one should be perfect with that. An application of Ampere's swimming rule to know the direction of deflection of the needle placed below a current carrying conductor. Coming to the next, left hand rule of Fleming, one should be perfect with. The central finger that gives you the direction of current, and forefinger that tells us the direction of the field, which is magnetic field, and thumb that shows us the motion produced in the conductor or the force that it is experiencing. So about this application one should be thorough with. In addition to that, the important most formulae of this topic, starting from Boyd-Sievert's law, Ampere's circuital law, the magnetic induction due to a straight current carrying conductor of infinite length and of finite length. Likewise, magnetic induction at a point on the axis of a circular current carrying a coil. All these concepts one should be thorough with. In addition to this, what is the force between two straight current carrying conductors parallel to each other? It's of course mu naught by 2 pi I1 I2 L over D. L is the length of that wire and D is the distance of separation between the straight parallel current carrying conductors. So that is one particular equation, of which once again 2-3 more applications are also there. All those you are supposed to be familiar with. Coming to the last phase of this chapter, we have to remember about tangent galvanometer, moving coil galvanometer. What are their principles? With what maximum value rather we can measure with utmost accuracy? Which one out of those two is more accurate and why? In fact, moving coil galvanometer we used to say that it's more accurate than tangent galvanometer. What are the features? Why it is like that? All those points we have to remember. Coming to the last in this order, we need to know how to convert a moving coil galvanometer into an ammeter and a voltmeter. After that, what is the current sensitivity of an ammeter? What is voltage sensitivity of a voltmeter? All those concepts you people might have already taken up, but all those formulae and theoretical concepts related to them are supposed to be remembered before taking up this particular chapter, magnetic effects of electric currents. So taking all these applications into account, we have picked up few problems which of course some of them have appeared in the previous EEE papers, IIT screening papers and IIT main models like, and few additional questions of different models also we have included. All those problems we are going to take them up one after the other, and whatever the relevant theory that we need to do that particular problem there, I'll just explain you that one then and there itself, so that all of you can recollect what you have read related to the same concept regarding that particular problem as such. So with this, let us start few problems of this chapter and work them out one after the other. Let me take up the very first formula. First problem based on the equation, which of course is magnetic induction at the center of a circular current carrying a coil. Now let me read out the first problem here. If in a circular coil A of radius r, current I is flowing, and in another coil B of radius 2r, a current 2I is flowing, then the ratio of the magnetic fields BA and BB produced by them at their respective centers will be how much? And options are given this way. The first option is 1:1, second option is 2:1, third option is 1:2, and fourth option is 4:1. And the correct option for this particular problem is the first one, 1:1. But let me just remind you what exactly the concept he is asking. He is just describing two different circular coils. One circular coil, according to him, is having a radius r and it is carrying a current I. There is one more circular coil over here with greater radius here, that is 2r, and it is now carrying a current, say 2I. You definitely can understand this O is its center and O dash is the center of the second one. Now what is the magnetic field ratio at this center and at this center? That ratio we just want. Now all of you are familiar with this formula. Magnetic induction at this point, which is the center of the first circular coil, that BA is equal to mu naught by 2 Ni by R. N being the number of turns, I being the current passing through that, R being the radius of the coil. And if you look at the same concept over here, magnetic induction at the center of the second coil. This is first coil, this one the second coil for us, according to the description given in the problem. So this is now going to be mu naught by 2 N into current is 2I and radius is 2R. N into 2I by 2R. So all of you can understand 2 getting cancelled here. Are you not having once again mu naught by 2 into Ni by R only? But in this particular case, number of turns he has not mentioned. Not mentioned means you just have to take them to be same, or it may be a coil having a one turn only. So whatever be the case, it hardly matters. When you look at these two values, they are exactly one and the same. So what can we write now? B at the center of A is to B at the center of B. Is it not simply 1:1? So if you look at all the 4 options mentioned over there, the first option only is 1:1. Therefore, the correct answer for this particular problem is going to be the first option, which is A in this particular case. So this is the very first problem which in fact has been given in 2002 IEEE paper. So if you look at this, certainly you can understand the center, at the center of a circular coil, what is the general formula for magnetic induction? It's mu naught by 2 Ni by R. That is actually the formula. Suppose if you take the point is right on the axis of that circular coil, then the formula is slightly different. You all know that is also a special case there. Mu naught by 2 Ni R square by R square plus D square whole power 3 by 2. That D is the distance to that point of consideration taken right on the axis of that circular coil as such. From that only we have taken up this equation. You must all be knowing that one very well, I hope. So the correct answer for the first problem is 1:1, which is tallied with the very first option given, that as A. That is first problem as such. Let us consider the second problem, which also has been given in 2002 IEEE paper, but one of the excellent model questions what we have. Let me read out the question. Wires 1 and 2 carrying currents I1 and I2 respectively are inclined at an angle theta to each other. He is just giving us two wires. One wire is a straight wire taken this way. One more wire is given with slanting, like making an angle theta here like. This he is said as the first wire, this he has given as the second wire. That is what he is giving in the first sentence. Let me continue. The force on a small element dl of wire 2 at a distance r from the first wire due to the magnetic field of the wire 1 is how much? If you look at, this is the distance given as r, this is a small element of length dl, and this angle of course is right angle according to the figure that has been mentioned there. And what did he say? This first wire is now carrying a current I1, second wire is now carrying a current I2. This is what has been given. And what is his question there? When you consider a small element dl, that too in the second wire, from the first wire at a distance r we are considering this element of length dl. Due to the magnetic field produced by this current I1, what is the force that is acting on the element dl? That's what is the question. In fact, force due to the current, and that too current carrying conductor when it is placed in a magnetic field. We all know that one as BIL sin theta, the formula generally. If it is the maximum force that is expected over there, it will now be BIL. We know that point very well. Based on the same concept, you can simply write the formula here. This dl is now making an angle theta with this particular direction. Then what will now be the force? You can directly write that one. Mu naught by 2 pi I1 I2 dl cos theta over r. That's all. So if you take its component this side, that is enough. So what will be that value? Dl cos theta by r, mu naught by 4 pi into I1 I2 dl cos theta by r. Which option that is correct over there you look at? First option is given mu naught by 2 pi I1 I2 dl tan theta by r. Second option mu naught by 2 pi I1 I2 dl sin theta by r. And third option he says mu naught by 2 pi I1 I2 dl cos theta by r. And fourth option mu naught by 4 pi I1 I2 dl cos theta by r. That means which option is correct over there? The third option is going to be correct. So the answer for this one is directly C. This is what you people have to remember. This is a wonderful concept he has given in 2002, right? That one has to remember such models thoroughly. So this is our second problem, of which the correct option is C as given in the problem as such. Let us check problem number 3. A particle of mass m and charge q moving with velocity v describes a circular path of radius r when subjected to a uniform transverse magnetic field of induction B. The work done by the field when the particle completes one full circle is how much? He has given 4 options once again. First option says mv square by r whole multiplied by 2 pi r. Second option of course is given 0. Third option is bq into 2 pi r. And fourth option is given bqv into 2 pi r. In fact, the correct option over here is the second one, that is 0. First thing you should understand from the description, whenever a transverse magnetic field is applied, what is the concept of transverse magnetic field here? The magnetic field which has been applied perpendicular to the motion of the particle. That transverse magnetic field, when you apply on any particle of some charge, either positive or negative, there is a possibility for that particular particle to trace a curved path there. When theta is exactly 90 degrees, that is when the magnetic field is perpendicular to the direction of motion of the particle, then surely the particle traces a circular path. We can understand well when you consider a particle is just moving along a circle of radius r, for example. Then what must be the basic condition for the particle to trace circular path? That centripetal and centrifugal forces acting on that particle are supposed to be equal and opposite. That's a basic condition needed for a particle to continue its motion along a circular path. But all of you can understand, in this particular case, the centripetal force is caused by the magnetic field. What is the formula for the centripetal force? It is BQV. B is the magnetic induction applied over there or field applied, and Q the charge of the particle, and V the velocity of the particle on the same circular track. So what you should understand here is, the question asked, you look at first, the work done by the field. Which field it is? Magnetic field. When the particle completes one circular rotation, one full circle. So all of you know from the concepts of rotational dynamics, work done by centripetal force acting on a body moving along a circular path in uniform motion is 0. I repeat, work done by centripetal force is 0 when a body is in uniform circular motion. So you can certainly understand this centripetal force is caused by magnetic field, and we can now write directly work done by centripetal force. Work done by centripetal force is 0. And centripetal force is caused by what? Magnetic field. Therefore, you can once again say work done by the field is 0. That's what he is asking you to calculate. No need for you to calculate anything. Only thing you should understand is the field is causing centripetal force required for the particle to continue its motion along the same circular path. That particular centripetal force does no work. means the field, the work done by the field in this case is going to be 0. So we can say the correct option over here for this particular problem is B now. So work done by centripetal force, since it is 0 and centripetal force is caused by the magnetic field, then automatically work done by the field is definitely going to be 0. That is actually problem number 3 what we have, and correct option for this one is the second option, which says work is 0. The next problem says a particle of charge minus 16 into 10 power minus 18 coulomb moving with a velocity 10 meter per second along the x-axis enters a region where a magnetic field of induction B is along y-axis and an electric field of magnitude 10 power 4 volt per meter is along negative z-axis. So observe this wording carefully. Particle of some charge is moving along x-axis. Magnetic field that is acting on that one is along y-axis. The electric field acting on that particle is along negative z-axis. That means, can't you understand, all the three are mutually perpendicular to each other now. So if you people can say that this is the direction suppose taken by the particle, this is the magnetic field direction and this one is the electric field direction. That's what has been given. If you consider the remaining part of the problem, you will come to know what is to be calculated. If a charged particle continues moving along the x-axis, the magnitude of B is how much? Particle continues to move along x-axis means you can definitely understand initially also the particle was moving along x-axis. Now also the particle is undeviated from its motion, means it's continuing its motion along the same x-axis where actually along which actually it was entering into the magnetic field. That means you can understand here the particle's direction of motion is unchanged even after the application of magnetic field and electric field respectively. So what you should understand here, the force due to magnetic field, the force due to magnetic field and the force due to electric field, the force due to electric field, both acting on that charged particle are equal and opposite. That means what you should understand here, since the resultant force acting on the moving particle is 0, since the net force that is acting on the moving particle is 0, it is possible for that particle to move along the same x-axis without having any sort of a deviation. So what can we understand here? The force due to a magnetic field, which now is going to be BQV by formula, and the force due to electric field, which now is going to be E into Q, that is the formula. So this is the force formula that is due to the magnetic field acting on that particle, and this is the force due to electric field that is acting on the particle. Now if I cut this Q here, then what should be the velocity? It should be E by B. In fact, this velocity, all of you must have read that one as selective velocity, we call it. Whenever the velocity of the particle is selective, then it should be numerically equals to the ratio of electric and magnetic fields applied on the particle. So if you just take up E by B, then what is the value of B, the question? Is it not E over V now? What is electric field applied on the particle? It's given 10 to the power 4 volt per meter. What is the velocity with which the particle was moving there given? It is a 10 meter per second given. So if you cut this one thrice, then what will be the value of B now? It's 10 cube Weber per meter square. You can write directly, right? Or you can even call the same as Tesla. But of course here all the options are given in Weber per meter square like only. So see the first option, 10 cube Weber per meter square. What is the second option? 10 to the power 5 Weber per meter square. Third option, 10 power 16 Weber per meter square. And fourth option, 10 power minus 3 Weber per meter square. So you can certainly understand in this particular case, the correct option is A itself. So you can write the answer as the first option, that is A. Look at once again, BQV, that is force due to magnetic field, EQ, that is a force due to electric field. These two are supposed to be equal for the particle to continue its motion without having any sort of a deviation from its original path. Now in this case, initially the particle was entering along x-axis. Now also it is moving along the same x-axis, means its path is undeviated. The path undeviated means that itself is an indication that velocity must be E by B. That is the formula based on which we have calculated the value of magnetic field that is applied on the particle. So probably all of you might have got this one. The correct answer for this one is 10 cube Tesla or Weber per meter square. The correct option is A. That is problem number 4 for us. The next problem is problem number 5 for us. This problem is having a concept of magnetism also directly is involved. Let me read out the problem. A thin rectangular magnet suspended freely has a period of oscillation equal to capital T. Thin rectangular magnet. That word thin means its length can be taken into consideration, but not the breadth. Breadth is very much less when comparing to the length of that magnet, even though it is rectangular by shape. That's what he is talking. And come to the remaining part. Now it is broken into two equal halves. First of all, remember, a magnet is broken into two equal halves, means you can cut that one along its length into two pieces, or you can cut along with its breadth into two pieces. But what is the way he has cut? He has given it. Each having half of the original length. That means we have cut the magnet into two equal halves this way. That's what actually he is mentioning. And one piece is made to oscillate freely now in the same field. If its period of oscillation is T dash, the ratio T dash by T is how much? Way back in 2003, JEE paper, he has given this question. Now the options are given this way, 1 by 2 root 2, that is the first option. 1 by 2, that is the second option. Simply 2, that is 2:1 like ratio like, right? That is the third option. And 1 by 4, that is the fourth option. But one thing you can understand, as far as this problem is concerned, the correct option is B, that is 1 by 2. T dash by T is equal to 1 by 2, that is actually the correct answer. But how come? Look at, first of all, he is talking about magnet is oscillating. Magnet is oscillating means certainly it is an application of vibration magnetometer. So what is the formula for time period of a vibrating magnet or oscillating magnet? 2 pi under root I by m BH. That is the formula. You can all identify what is what out of it. I is moment of inertia of the magnet which has been used there, and capital M is its moment, magnetic moment we call that one, and BH is horizontal component of Earth's magnetic field. At a particular place we know that is a constant, and at a particular place on Earth we consider the magnetic field as uniform field also. Now this is the formula in which 2 pi is a constant, BH is a constant. Forget these constants now, eliminate them. Then what can I write? From this equation, time period t is proportional to under root I by m I can write. Now suppose if I take t dash by t, or t first I write, t is proportional to root of I by m. What is I over here? In fact, I is equal to m L square by 12. Observe this point carefully. Actually speaking, m into L square plus b square by 12 for a rectangular magnet. But he said very clearly in the problem, it is thin magnet. Thin magnet means what? Breadth need not be considered. Then what will be the formula? Simply ml square by 12. This is the formula we have to remember. Now look at this first t is proportional to I by m under root. T dash when I write, it is proportional to I dash by m dash, like I can write. But you can understand well, I is ml square by 12. Then what will be this I dash? When you are cutting the magnet into two equal halves, won't the mass becomes half now? When you are cutting it into two equal halves lengthwise that way, you can understand length is also becoming half now. So what I can write now? This now becomes L by 2 whole square, ml square by 12. That is the formula for I dash. So what we can write in this particular case? Is it not I over 8? So what is the relation between I dash and I? Now you can guess it. I dash is equal to I by 8. And what about this m dash now? You can certainly understand when you cut the magnet into two pieces, either lengthwise or breadthwise, whatever it is, you will be finding the magnetic moment becoming half. When magnetic moment is becoming half, you can directly write it is equivalent to m by 2. Now just write the ratio whatever we want. What is it we want? T dash by t I want. This now is under root I dash by I into m by m dash. So what are the values here? I dash by I is 1 by 8. M by m dash is 2 whole under root. It's now 1 by 4 under root, which now is 1 by 2. So what is t dash by t now? 1 by 2 is the correct ratio. So which option is tallied with this value? Second option in the problem is given 1 by 2. So you can directly write in this case, the answer for this problem is B. Only thing you should remember for this model question is this formula for time period of an oscillating magnet. T is equal to 2 pi under root I by m BH. I becomes moment of inertia and BH is horizontal component of Earth's magnetic field at that place where you are performing that experiment, and capital M gives you magnetic moment. That is the point. So the correct answer for this particular question number 5 is 1/2, which is the second option for us. Let us check the question number 6. Sixth problem has been given this way. A long wire carries a steady current. It is bent into a coil of 1 turn and the magnetic field at the center of the coil is B. It is then bent into a circular coil of n turns. The magnetic field at the center of the coil will be how much? That of course he has given the options. First option n times B, second option n square times B, third option 2n times B, and fourth option 2n square times B. And this was the question given in 2004 AIEEE paper. One of the wonderful models again. And correct option for this problem is the second one, that is n square times B. First thing what you should understand here is there is a circular coil like this. At the center O, what is magnetic induction? We all know that. Mu naught by 2 Ni by R. When I is the current that is passing through this coil, and when R is its radius like, then what is the magnetic induction at the center? And N of course gives you number of turns what this particular coil has got. But here in the beginning he said N is equal to 1. So N is equal to 1, we can write B is equal to mu naught by 2 into I by R. That is actually the formula for the first part. What is he doing? He has taken the same wire and wrapped that one into a coil of n turns now. Simple logic. When a wire is made into 1 turn or 2 turns or 3 or 4, whatever it is, the total volume should remain the same. Means what? 1 turn, radius R. Suppose if I make 2 turns, radius becomes R by 2. If I make that one into 3 turns, radius becomes R by 3, and so on. So what you should understand now, when made into n turns, then what will be the value of B dash? That's what I want. Mu naught by 2 constant will be the same. This n is the number of turns now. By R becomes R by n. That is a point what one has to understand. When you make 2 turns, R becomes half. 3 turns, R becomes 1/3. 4 turns, R becomes 1/4. N turns, R becomes 1/nth. Then automatically this becomes n square times mu naught by 2 I by R. That is nothing other than B. Therefore what we can write? B dash must be n square times B. So if you look at all the 4 options, the second option is exactly the same given, n square times B. So correct answer for this one now is going to be B as such. So only thing you should understand for this is, when 1 turn we take, the radius is R for example. When it is made into 2 turns, radius becomes R by 2. N turns, radius becomes R by N. Then automatically the magnetic induction at the center now becomes n square times the original value. So n square times B is the correct magnetic induction at the center of that particular coil having n turns which have been made over there now. So the correct answer for this problem 6 is going to be the second option, which is n square B. So option is B for it. Now the next problem is problem number 7. The magnetic field due to a current carrying circular loop of radius 3 centimeter at a point on the axis at a distance of 4 centimeter from the center is 54 microtesla. What will be its value at the center of the loop? That is a question asked. It was given in 2004, AEEE paper again. And first option is 250 microtesla. Second option is 150 microtesla. Third option is 125 microtesla. And fourth option is simply 75 microtesla. The correct answer for this one is A, which is 250 microtesla as such. Let me first of all give you what is he giving us. There is a circular current carrying coil like this, carrying some current I like this, and this is going to be the radius, and this is the axis. There is a point P which is at a distance D, that is 4 centimeter from the center, and radius is given 3 centimeter for us. This is the center of the coil. And we know pretty well this is going to be the direction of magnetic induction over there. What is this value that is provided? 54 microtesla he gave. So what is the formula for that one? First of all, B is equal to mu naught by 2 Ni R square by R square plus D square whole power 3 by 2. That is actual formula. All of you can understand. N being the number of turns there, I being the current that is passing through that, R is the radius, D is the distance to the point considered on its axis from its center. So now you can directly write what is the value given. This value is given 54 microtesla. And what is it he is asking us to calculate? He is just asking us to calculate B1, that is at the center. At the center, what is the formula? Mu naught by 2 Ni by R we want. What is that value is the question he is asking. So first of all, R value is given 3 centimeter and D value is known to us as 4 centimeter. So let us write the same thing this way. Mu naught by 2 Ni into R square. It's 9 into 10 to the power minus 4. You can all understand this is R square plus D square whole power 3 by 2 is nothing other than root over R square plus D square whole cube. R square 3 square, D square 4 square. Adding 25, root 25 5. This is 5 centimeter total, 5 cube. It's now going to be 125 centimeter cube. So you can write 125 into 10 power minus 6. Meter cube I should convert that one into. So you can directly write this is given as 54 microtesla. Answer also is given in microtesla. Therefore, no need for you to convert this one anymore. As it is, you take this one as 54 itself. Now here if you look at mu naught by 2 into Ni by R I want. So simply take what is mu naught by 2 into Ni from this particular part. What is that value? 54 into 125 into 10 power minus 6 divided by 9 into 10 power minus 4. This cancels minus 10 power minus 2 times. This goes 6 times. So what is it you people are getting here? 6 times 125 into 10 power minus 2. That is the value of mu naught by 2 into Ni. That value you write it here. So what will you get now as B1? 6 into 125 into 10 power minus 2 divided by R. R is given 3 centimeter. Write 3 into 10 power minus 2 meter. This 10 power minus 2 gets cancelled. This goes twice. So exactly 250 microtesla. That will now be your answer. So 250 microtesla, if you look at in the 4 options, very first option itself is tallied with that. So what is the correct answer for this problem now? It is A, the very first option, that is correct now for us. So you should understand in this case, mu naught by 2 ni r square by r square plus d square whole power 3 by 2. That is the formula for magnetic induction at a point on the axis of the circular current carrying coil, which is at a distance d here now. But what is his question there? He is asking you what is its value at the center. At the center means this is the formula. Now simplify the method, whatever you want to adopt, it is left to you, whichever method you want to adopt, but ultimately our result should be the same. The result is 250 microtesla here, which is the very first option that is going to be correct for this problem number 7. Problem number 8 is based on 2 concentric circular coils carrying currents he has given. Let me read it out. 2 concentric circular coils, each of radius 2 pi centimeter, are placed at right angles to each other. Currents of 3 ampere and 4 ampere are flowing in these coils. The magnetic induction in Weber per meter square at the common center of these 2 coils will be how much? Way back in 2005, in AEEE paper, he has given this question. First option is 5 into 10 power minus 5 Tesla. Second option is 7 into 10 power minus 5 Tesla. Third option is 12 into 10 to the power minus 5 Tesla. And fourth option is simply 10 power minus 5 Tesla. Correct option for this one is the first one, 5 into 10 power minus 5 Weber per meter square or Tesla there. What is he talking? First of all, 2 concentric circular coils, each of radius 2 pi centimeter, are placed at right angles to each other. You can understand one circular coil is this way and the other circular coil is this way, this being their common center. Now you can definitely understand both are, according to him, carrying 3 ampere and 4 ampere currents. So here this is 3 ampere current and this one is 4 ampere current. That's what he is talking about. This is their common center where he wants us to calculate the magnetic induction. And one thing more he gave, the radius for this one as well as for this one, they both are equal and radius is given 2 pi centimeter for both of them. So you can understand well the magnetic field due to one particular circular coil is perpendicular in direction to the magnetic field due to the other circular coil. I hope you might have followed this point. Both the magnetic fields which are produced at their common center are certainly going to be mutually perpendicular to each other. When they are mutually perpendicular to each other or when the angle between them is 90 degrees, what would now be the resultant magnetic field at the common center? It's B1 square over B2 square plus B2 square under root. B1 square plus B2 square under root is going to be the resultant or net magnetic field at that center, which is common for both of them. Now you can understand what is the formula for B1. It's mu naught by 2 Ni by R. I1 I can write. And you can now understand the next one over here. What about B2? mu naught by 2 n I2 by R. But he did not mention here the number of turns. Means one should understand either both may be having the same number of turns or each one is a single turn it is having like. Then no problem. No need for us to take this value of n anymore. Now if you substitute these two values there, what will you get for the resultant magnetic field? Mu naught by 2 whole square you can bring it out. Mu naught by 2r you can totally get it out into root of I1 square plus I2 square. In fact, mu naught is 4 pi into 10 power minus 7 by 2 into 2 pi into 10 power minus 2. Because radius is given 2 pi centimeter, you can convert that into meter by multiplying it by 10 power minus 2. So this into root of I1 square plus I2 square, that now becomes simply 5. It is I1 square 9, I2 square 16, 9 plus 16, 25 under root is now going to be 5. Now here 10 power minus 5 times it goes. 2 into 2 pi is 4 pi, that gets cancelled. So what is now left over? 5 into 10 to the power minus 5 Weber per meter square. That should be the correct answer for us. What are the 4 options given? You check once. First option is 5 into 10 power minus 5, which is our answer actually. And second option, as I said, 7 into 10 power minus 5. Third option 12 into 10 power minus 5, and fourth option simply 10 power minus 5. So what is the correct option here? The very first option is going to be correct here, that is option A. But only point you should understand here is, since both the coils are mutually perpendicular to each other, the magnetic induction fields at their common center also are going to be mutually perpendicular to each other. So considering that particular aspect, we have calculated taking this particular value, root of b1 square plus b2 square will now be the resultant value of b or the net value of b there at that particular point. So the correct answer for this one is the very first option, which is 5 into 10 to the power minus 5 Weber per meter square as such. That is problem number 8 for us. Problem number 9 says, two identical conducting wires AOB and COD are placed at right angles to each other. The wire AOB carries an electric current I1 and COD carries another current I2. The magnetic field on a point lying at a distance d from O in a direction perpendicular to the plane of the wires AOB and COD will be given by how much? This was given in EEE paper in 2007. And correct option, of course, we shall discuss later. First of all, what are the options given? Let us check. First option, mu naught by 2 pi I1 plus I2 by d whole to the power half, that is under root. Second option, mu naught by 2 pi d into I1 square plus I2 square whole power half. Third option, mu naught by 2 pi d into I1 plus I2. And fourth option, mu naught by 2 pi d into I1 square plus I2 square. The correct option for this particular problem is the second option, which is mu naught by 2 pi d into I1 square plus I2 square whole power half. What exactly the concept he is talking about? Let us check first. He is just giving us two wires which are mutually perpendicular like this. This is the point O. This one is AOB. This one is say COD like. Both, of course, he said they are carrying currents I1 and I2 respectively. Now the concept here is they are like this now. You should understand. Now from O at a point D, that particular point D means perpendicular to both the plane in which both the wires are lying. That's what the condition he has mentioned. So when this one is one wire, this one is the other wire, perpendicular to that one means either that one should be outside the board or inside the board. If I consider this is the point above this, at a particular distance D, what is going to be the magnetic induction at that point of consideration? That is the question he is asking. But in true sense, we know the magnetic induction due to a straight current carrying conductor of infinite length. We know directly the formula this way, mu naught by 2 pi into I by R. That is actual formula what we know. So what we have to calculate here is what is a magnetic field due to AOB first. That's mu naught by 2 pi into I1 by D. That is the first formula. And of course B due to COD at that same point, mu naught by 2 pi, directly we can write, into I2 by D, we can write like this. But again you people can understand, since these two are mutually perpendicular to each other, the magnetic field produced also will be mutually perpendicular to each other. Magnetic fields produced by both of them, they are also going to be mutually perpendicular to each other. Then what can we write? The resultant or net magnetic field, that now becomes B due to AOB square plus B due to COD square, whole under root. So what can we write now? Directly we can take mu naught by 2 pi D. Because mu naught by 2 pi whole square, if I take common and I can take it out. Likewise 1 by D square also I can take it out. Into root of I1 square plus I2 square. That only he has given in the problem mu naught by 2 pi D, right, into I1 square, capital letters he has given, I2 square whole to the power half. To the power half means under root only, every one of us we know. This is correct answer for us for this problem number 9. So which one is exactly tallying with this one? The second option is tallying with this one. So we can write answer for this particular problem is B as such. So 9th problem has got second one as its option, mu naught by 2 pi D into root of I1 square plus I2 square or I1 square plus I2 square whole per half. That's what actually we have to remember. So this is problem number 9 what we have. Now let us check problem number 10. This has been given in screening examination of IIT in 2002. Wonderful model he has mentioned here. A particle of mass m and charge q moves with a constant velocity v along the positive x direction. It enters a region containing a uniform magnetic field B directed along a negative z axis extending from x is equal to a to x is equal to b. The minimum value of velocity v required so that the particle can just enter the region x is greater than b is how much? Only thing you people should understand what is the very meaning of it carefully, that's all. Question is a simple one. A particle of mass m and charge q moves with a constant velocity v along the positive x direction. It's moving along x axis, you can directly understand from the first sentence. It enters a region containing a uniform magnetic field B directed along negative z direction, right? In what way it is extending? He said extending from x is equal to a to x is equal to b. That means the total distance. This particle of course is going to be influenced by the magnetic field is b minus a. From a to b, that is the concept. So b minus a is the total span or the space in which the influence of that field is observed as far as this particular charged particle that is concerned. And what is this question? What is the minimum value of v that is required? Minimum value of velocity that is required, he is asking you. So you can definitely understand in this particular case, this is problem number 10 we people are discussing about. Centripetal force that is caused by the magnetic field. For the particle to continue its motion in any circular orbit or anything like, minimum condition needed is that centripetal force and centrifugal force are supposed to be equal. So the centripetal force here is caused by the magnetic field. That now must be equal to centrifugal force, which of course by formula we all can write mv square by r. Centripetal force is caused by the magnetic field. Centrifugal is a fictitious force which is supposed to be equal to the centripetal force for the particle to continue its motion along a circular path. Now his concept here is mv square by r is bqv, then one v I can cancel it. And what is the value he is asking? Velocity he is asking you. Is it not bqr by m now? Only thing you should understand here according to the values given, r now should be equal to b minus a. That is the only thing you need to understand. So directly you write what will be the velocity. V is equal to bq into b minus a divided by mass. This is supposed to be the velocity of the particle. Which option of course is given like that? You check it. First option he gave qbb by m. And what is the second option? Q into b minus a into capital B by m. Third option he said q small a into capital B by m. And fourth option he has given q into b plus a into capital B by 2m. What is the correct option here? Q into b minus a into capital B by m. So the correct option that has been given here is B again. So what is the correct answer over here? It is the second option given out of the 4 in this problem number 10, that is the correct option for us. And all of you should remember, the moment magnetic field is perpendicular to the direction of motion of the particle, which is charged, then automatically it traces a circular path. And what is the condition for a particle to trace circular path? That the centripetal and centrifugal forces acting on that particle are supposed to be equal. And in this particular case, centripetal force is rather due to the magnetic field applied. And centrifugal force is supposed to be equal to this and opposite by direction. And it is a fictitious force, we know that. And its value can be taken by that formula mv square by r. Simply equating them, you can achieve your answer. One of the excellent questions given in the year 2002 in IIT screening paper. This is question number 10.